Okay, so we're going to start to go over the study guide, and I think we're going to start from the back and work our way forward. So if you go, and let me go and present the screen here, hopefully. Okay, so if you go to the very last part of the study guide, that's where we're going to start. Okay, and specifically this question, which, what is this? Is this number 28? Is that right? Number 28? Okay. So this is number 28 on the study guide. Okay, and it says that you've got a piece of metal weighing 59 grams and it was heated to 100 degrees Celsius, then put into 100 milliliters of water. That was initially at 23.7 degrees Celsius. Now the metal and the water were allowed to come to an equilibrium temperature determined to be 27.8 degrees Celsius. Guys, this was the experiment that we did right before all of the snow and ice hit. We did the same kind of thing with a piece of copper or a piece of carbon steel. This is the experiment that we did. Okay. So the question says here, was the reaction for the water endo or exothermic? Explain how you know. Okay, you could probably answer this question without ever having to do any kind of math, right? If you're taking cool water and you drop a piece of hot metal into the cool water, okay, so the hot metal goes in. What's going to happen to the hot metal's energy? Yeah, it's going to heat the water up. That hot metal is going to leave, or the hot energy is going to leave the metal. It's going to go into the water. So the energy leaves the metal, goes into the water. So you could say that water is gaining energy. It's absorbing energy. So would we call that endo or exothermic for the water? It's endo. Yeah, for the water, For the metal, it's exo. For the water, though, the water is gaining the energy. So for number two, well, it says number 2 here, but for the water is gaining energy. So we would say that is endothermic, yikes. Endothermic. The water is gaining energy from the metal, so we call that endothermic. The third part here, which on your paper is letter B, says assuming that no heat is lost to the environment, calculate the specific heat of the metal. Okay, so what we could do here is just set up a giant heat equation, because if you remember that heat gained by the water is equal to heat lost by the metal. Heat gained is equal to heat lost. So we're just going to set up an equation with everything that we know, okay? So let's do our water side first. That's going to be our water side. So we need to know 3 things about the water. You have to know the mass, the M. You have to know the specific heat of the water, and you have to know the change in the temperature of the water, right? So we're going to do our water side, our heat gain. So the mass of the water, they tell us here. You guys see it? Oh. They don't tell us the mass, but they do tell us this right here. And we have 100 milliliters of water, okay? I'll try to remember to put this on the test, but if you know that the density of water is about 1 gram per 1 milliliter, if you had 100 milliliters of water, what would the mass be? 100 grams. So we have 100 grams of water. So this is 100 grams of water, H2O. So we know our mass. Our specific heat of water, did I not put that on there either? Nice, okay.
4.
Yeah, it's 4.18. So the specific heat of water is 4.18. I'll try to put that on there tomorrow too. Maybe I'll remember. Anyways, the specific heat of water, so the CP of water for H2O is 4.18 joules per grams degrees Celsius. That would have been nice to know, huh? 4.18, there's our specific heat of water. And then you need the delta T, the change in temperature. What is change in temperature based on? What 2 things? Good, temperature final minus temperature initial, right? So we need the final temperature of the whole system, which they said the metal and the water were allowed to come to a temperature determined to be 27.8. So we're going to do 27.8. There's our final temperature of the system minus the initial temperature of the water, which they said was, where's that? Oh, 23.7. Yeah. Okay. Great. I forgot to put that in there too. Okay. So there's our delta T. You what?
That would make it very.
Yes, that would be the worst problem ever. Okay. So now we can go ahead and let's go ahead and set up our other side, and then we'll just do all the math at one time. So there's our water side. What we just completed is the water side. That's the heat gained by the water. Let's set up our heat loss side. Heat loss, we got to be talking about the metal, right? So the mass of the metal, they said here, is 59.047 grams of the metal times what comes next? Specific heat of the metal. Good. And that's what we're trying to find out. Thank you. Yeah, that's what we're trying to find out. Don't know that. And we do know, though, the change in the temperature, right? The metal, they tell us here, it was initially heated, the piece of metal was initially heated to 100 degrees Celsius. So they got it up to 100 degrees Celsius, and then they dropped it into water to let it cool to a final temperature of 27.8. That's the final temperature of the system right there. So how would we set these numbers in here? I think I would do opposite. Yeah, because I would do final minus initial. So 27.8, that's my final temperature of the system, minus the initial temperature of the metal, which was 100. Now that is going to give us a negative number on that side, right? How are we going to fix that, though? Right. Do you remember this right here? I was talking about that. You represent that heat is lost by going ahead and just assigning that a negative value. Okay. So virtually all it's going to do is cancel out that negative sign, right? You're going to end up with a positive number in the end. Okay. So here we go. Let's go ahead and solve this. You're just going to to find CP at this point. So I'm going to do all the math on the left side. I'm going to do 100 times. And you guys better double check me. It's been a rough morning. Times 4.18 times the change in temperature. So 27.8 minus 23.7. I got 1,713.8 is equal to, so we good so far? Is that what you guys, hey, Jacob?
Yeah, I got 1,716.26. I got what you got.
Okay. I don't know. Yeah, I think I put everything in right.
Yeah, I know what you got.
Okay, we're gonna go with mine. 3 out of 4. All right. And again, science is close enough, Jacob. I mean, it's fine probably. So we're not sending rovers to Mars. It should be all right. Okay, 59.047 grams, 0.047 times. I'm gonna do 27.8 minus 100. And I got negative 4,263. And I have a negative right here in front. So negative times a negative is going to turn that positive. So I'm just going to go ahead and let that be a positive number. So 4,263.2 times CP. Now at this point, what do you do with your numbers?
Divide the one with CP.
Yeah.
Divide that number.
Right. You divide both sides by the one that's attached to CP. So you're going to divide everything by 4,263. And you end up with 0.402. So I'm going to write it here. CP ends up being 0.402. When you talk about specific heat tells you the amount of heat, the amount of energy that it takes to do what? Yeah, to raise it by 1 degree. 1 gram by 1 degree. It's the amount of energy So the amount of joules it would take to raise up the temperature by 1 degree Celsius for every 1 gram that you have. So that's the units, right? It's energy per grams degree Celsius. All right, so there's your specific heat for that one. All right, at this point, do you know where all the numbers came from? Do you understand where we got all the numbers? All right. So there's 28. Hey, what happened to my numbering here? 27, and then it goes to 21. Nice. All right, let's do 21, which is technically 29. Let's go ahead and, yeah, it's the last one on that page. The following are enthalpy values. So that one, it's right underneath number 28. Let's go ahead and look at that one. Okay. So the following are enthalpy values for 1 mole of each substance, okay? What's the change in enthalpy for the reaction? All right, so this formula was the enthalpy formula that, again, it was in the notes from a few weeks ago, but basically, and I think maybe this was from our snowcation, the notes from the snowcation that we had. Okay, you have your enthalpy. It's going to be equal to, and this is the formula with all the weird signs in it, but basically it's the sum of the moles or the coefficients of the products, the coefficients times the product's enthalpy, delta H, minus the sum of the moles, the coefficients times the delta H of the reactants. Which looks like a lot, but this is a super easy formula to use because all you're really doing is adding up numbers and then subtracting them. Might have to do a little bit of multiplication. Okay, so here you go. These values right here at the top, those are the enthalpy values for the substances in this particular reaction. So this right here, this is the reaction that we're going to be looking at. NO plus O2 yields NO2. And the question says, what is the change in enthalpy for the following reaction? Okay, be sure to balance your equation first. You always start with balancing the equation, right? So if you take a look at that, how would we go about balancing that equation? Yeah, 2NO. Okay. And if you do that, if you put a 2NO and a 2NO2, that's going to balance out the ends and you'll have 4 oxygens on both sides, right? Okay, so now that we've got that, another thing that I like to do when I'm trying to solve these problems is actually go and label my enthalpies and go ahead and multiply and do whatever I'm going to do. So on my product side, my products, I'm going to start with those first since that's what I'm going to have to put in my formula first. My NO2, I'm going to go up here and I'm going to find the value of enthalpy for NO2, which they tell me is 33 kilojoules. So I'm going to go ahead and do 2 times 33. Oops. So there's my products. So I'm going to go ahead and write this in. I'm going to say delta H is equal to the sum of all the products. Of course, there's only one product here, but I'm going to do 2 times 33, which is going to be 66 kilojoules, minus, I'm going to have to find the sum of all the reactants, right? So on this side right here, here are the reactants. So I'm going to go find my NO, which I look up here. I'm going to say 90 times 2. So it's 180 plus O2, right? If you look up here, O2 is called a standard state element. It's just an element in its standard state. O2, N2, H2, all of the diatomic molecules, anything that's just a single element in its standard room temperature state of matter is always going to be 0 kilojoules. Okay, but that's just 0. Okay, so there's no change in the heat of the reaction there. And so now at this point, you just solve it, right? So if you plug into your calculator, 66 minus 180, The change in the heat of the reaction or the change in enthalpy would be what? Negative what? 114. Negative 114 kilojoules. Okay. All right. Do what? Yeah, sure. Negative 114 kilojoules. Yes.
If I balance the equation too high and then, like I had 4 NO and 2 O2.
Did you get like 228?
Yeah.
Yeah.
Is that wrong then?
No. Because that would be correct. Now, the only problem is if this ends up being like a multiple choice question tomorrow, just realize that it's got to be one of the choices. You're just going to have to simplify it. And do you understand what he's talking about? On his coefficients, you did like 4, 2, and 4, maybe. Yeah. You always want to try to ask yourself, though, before you go into these problems, are the coefficients simplified? You do want to have the simplest form, but what you did is right. You're just saying you've got twice as much, like it's double the reactants and products. Okay. But in these situations, though, try to go ahead and simplify it before you start it. Okay. All right. Now, while we're here, though, the next question there on part B, it says, would the reaction be considered endothermic or exothermic? Exo, why? Kilojoules, that's right. It's losing 114 kilojoules of energy to the surroundings. So this reaction is going to be considered exothermic. And while we're here, if you did this reaction, how would the surroundings feel? They would start to get warmer. It would the surroundings would begin to feel warmer. What is this reaction? So the reaction to create nitrogen dioxide, NO2.
Which is what?
I don't know if it's like funny, like laughing gas, like dental, or is that?
Maybe.
And I don't know. Is that what you guys call it in Germany? It's called laughing gas here, right? You guys have to get the juice when you go to the dentist? I don't. I'm calm as a cucumber at the dentist. So, all right. Calm as a cucumber.
Just get annoyed by the feeling of the big stick in the top.
Yeah, that's no fun. Wait till you get older. Then they have this little water pick that they use on your gum line. Yeah, it's awesome. I have to go like every 3 months now. Yeah. Apparently it's a thing after you turn 40. Yeah, it's gross.
I have one braces.
Oh yeah, just to keep the stuff out. This is like, well, we won't go on into all of it because it's being recorded. But anyways, I'll tell you later. It's really gross. All right. Okay, so there's that. We've got just a couple more minutes. And I am going to go ahead and I will post the rest of the answers later that you can check them if you want to. But we've got just a couple of minutes. Let's see if we can do maybe another math problem. Just real quick to see that we got it. If you go and find, let's see, this is question 26 and 27, actually. So this is 26 and 27.
You're thinking of N2O.
That's laughing gas. So what's NO2? Did you look that one up?
It's a harmful gas produced by cigarette smoke and cars.
Oh, definitely don't want to have that one at the dentist. Yeah.
No.
So, Jacob,
It's also used in fertilizers.
NO2 is?
Yeah.
Oh.
What?
Yeah, fertilizers.
Yeah.
Huh. Yeah, right. Okay, so 26 and 27. Here we go. Number 26. How much energy is needed to change the temperature of 50 grams of water by 15 degrees Celsius? If they're asking you to calculate energy, guys, what's the symbol that we're using here for energy and heat? Q. So if they're asking you for energy, they're asking you for Q. So on number 26, this is going to be a Q formula. We're going to say Q equals, and we're looking at water again. Okay, so do we know the mass of the water? And the answer is yes, we do. We've got 50 grams of water. You have to know the specific heat of water, which I keep forgetting to put it on here, but it's 4.18. We've been using it a lot. Right?
Don't we also need the initial temperature?
No, I'm telling us to change.
Yeah. So yeah, be careful about that tomorrow in the reading. if it says that the change is this, they've already done it for you.
Okay.
Yeah, so that is the delta T is 15 degrees. And the fact that they said it changed by a positive 15 degrees, okay, that means it's absorbed energy. So we should have a positive Q, right? It changed by 15 degrees. Okay, so here we go. At this point, you just multiply, right? So if somebody's got a calculator or super fast, it's what?
3135.
3135. Nice. And what's the unit here? Joules. Yeah. So 3,135 joules. If,
That's incorrect.
what'd you get?
I got, 3,139.5.
That's what I got too.
3,139.5.
I put, wait,
I got three.
yeah, I got what Jacob got.
You got what Jacob got?
Times 4.18 times 15.
It's because some people did.
4.184.
Yeah.
Yeah.
Is exactly what's on the board.
Okay. Yeah. So if you do 4.18, it's 3135. If you do 4.184, it's something else. 3138. So again, though, like, I mean, you're talking a difference of like 3 joules of energy. That's not going to amount to anything. Science motto, everybody? Close enough. All right, good. All right, so that's good enough, close enough. 3,135, 3,138. Tomorrow, if this were a multiple choice question, guys, I'm not going to get anywhere, you know, like way off, more off than that. Like if it's, I'm not going to put 3,138 and 3,135. Like I'm not going to make you do that. Okay. All right. 27, what's the final temperature after 800 joules is absorbed by 10 grams of water, 25 degrees Celsius? Okay. So they're looking for TF this time, right? But they give you the joules. So what's that going to be? Where's that going to be in this equation? The Q, right? So you got 840 is equal to, you've got 10 grams of water times your specific heat of water, which is a known. And then you're trying to figure out final temperature, which is TF minus 25, your initial temperature of water, okay? Now at that point, it's just gonna become a multiplication or an algebra problem, right? So did anybody do that one? What'd you get?
45.07 degrees. Okay.
You got 45? Okay. Anybody concur, agree? Otherwise, he got 45. What'd you get, Dylan? Did you get the same thing?
Yeah.
All right. Yep. Nice. Okay. Hey, what's our unit? Perfect. There you go. All right. The rest of the answers will be posted later. If you would like to check it, you can. You can bring your study guide tomorrow. You can bring old homework because you know the virtual kids are. Okay. You just can't, oh, well, not all virtual kids probably, but make sure that you have your calculator tomorrow, have all that stuff ready to go. Vocabulary. Okay. Dang.
I will not be here tomorrow.
Oh, right.
I might have an internet connection, so I might be able to do it anyway,
Yeah.
but that's maybe.
Well, and if you can join the virtual meet, that would be good. It'll be at 8 in the morning.
Yeah, I'll probably